We want to graph a piecewise defined function, and it's important to remember here that we have a rule defining the y value, or h of x, for specific values of the input variable, which is x. So if x is equal to 0, right? If x is equal to 0, then h of x is equal to -4. And that's that point right there. And if h of x is not equal to 0, if x is not equal to 0, then h of x is equal to 2. In ALEX, it doesn't matter which order you use, but you graph this using the solid circle, and then you put the open circle in place, and then you plot your line, and it will leave the open circle blank. I want to do a couple of examples of this. We're given a rule for g of x, -x if x does not equal -2, and 5 if x does equal -2. So in this case, I'm going to plot my single point first. If x is equal to -2, then g of x is equal to 5. So this is this point right here. Now, if -2 were in the domain of this segment, we would have the point -2, 2. That's our hole, -2, 2. And then the graph of -x looks like this. It's a line. And so it's important here to know what graphs look like without having to plot points. Just know the graphs you have already seen. Okay, this is slightly more complex. We have 3 different segments of the domain. We have what happens if x is less than or equal to -2. Then h of x is -1. Okay, and then that's that segment. I'm going to do this segment next, just because I like to deal with the outer edges first. 3 if x is greater than or equal to +2. So this goes this way. And then I have x plus 1 in between. So that's this line right here with slope 1. And it attaches those two pieces. Now in ALEX, you have to put the open circle at the end in order to graph this point, to graph the endpoints and graph the line segment connecting them. But you don't want to leave these open circles here because there are not holes in this graph. Even though this graph is piecewise defined, it is continuous. Right? I can draw the whole thing without picking up my pen. So don't leave the open holes here. Make sure that those are solid.